take a look at an example where we need to integrate along the length of the wire to get the magnetic force on the wire. Let's start off with one that's straight though. Okay. So this one reads that we have a long rigid conductor lying along an x-axis, carries a current of 5 amps in the negative x direction. Magnetic field is present given by B is 3 in the I hat plus 8x squared in the j hat, with x in meters and B in milliteslas. So we got to watch out for that. So it's not Teslas but milliteslas. Find in unit vector notation the force on the 2 meter segment of the conductor that lies between x equals 1 meter and x equals 3 meters. So we have our wire lying along the x-axis. Okay. And what we're going to look at is 1, 2, 3. 1 meter, 3 meters. And so we're going to look at the 5 amps in the negative x direction, 2 meter long segment between 1 and 3 meters. So there's my wire, and it's carrying the current. .5 amps in the negative x direction, and it's in a magnetic field, and the magnetic field is given as 3 in the I hat, and then it's plus 8x squared in the j hat. Okay, so what that means is at y equals 0, then it's just 3 in the I hat at all points in through here. And then as we move to where x is 1, and 1 squared is 1, and 1 times 8 is 8, so it goes essentially up 3 but then over 8. So now it's pointing this way. Pretend that looks like it's 8. I don't think it looks like it's anywhere near long enough to be 8, but it'll be all right. And then when we're at x equals 3, 3 squared is 9. 9 times 8 is what? 72. So it goes up 3 and then over 72. So, okay. So, good thing we don't really need the vectors drawn in for the vector field. But it's not constant. That's kind of the big deal. Okay. So these are our magnetic field vectors, and they kind of change as you move along through the length of the wire. Okay. And so what we want to do is want to go ahead and find the force on this particular segment. Okay. And so then what we'll look at is we're going to go in and write down that our I'm going to go in and we're going to pick that our ds element is going to go in the positive x direction. So this will be essentially dx in the I hat. Now, since the current went the other way and the current just multiplies the ds, then what I will do is I will go ahead and make the value for I negative to reverse the direction. Okay, so the minus sign will be carried on the value for I here. So I'll make it -5 so that my ds will just be dx in the I hat. And I'm going to cross that into our magnetic field that's here. And the thing we have to remember is that this magnetic field, and I almost forgot again, was in milliteslas. So I'm going to put in my 10 to the -3 so I don't lose it. Because otherwise, by the time I get to the end, I'll forget that it was in milliteslas, not teslas. I'll forget the milli piece. So, all right. So then what we can do is we can go and write down that our magnetic force is going to be I times the integral of this ds cross B. and we're going to integrate along the length of the vector. So this is going to be my negative 5 amps. So there's the minus sign for the fact that it was going in the negative x direction. We're going to integrate from x equals 1 meter to x equals 3 meters. And what I'm going to have, 3 meters, is the ds is going to be our dx in the I hat direction crossed with 3 I hat plus 8 x squared j hat, and this is times 10 to the minus 3 for the milli. Okay, and so then what I'm going to do is I'm going to go in and I'm going to distribute the I hat to both terms, run the cross product. But I hat cross I hat is just 0. So that term cancels out, and I get I hat cross j hat, right? So I hat is going to be in this direction, points in the positive x direction. J hat points in the positive y direction. And if we do I hat and then crossed with j hat, either you sweep like this, or you put first vector, second vector, third vector, product, first, second, and then product. It comes out of the page, which is just going to be, k hat. So I hat cross j hat is k hat. I think you probably knew that one, but I always like to check, because not always are they real obvious, and they can reverse orders on you, and you just gotta check. So then what we get here is that our magnetic force is going to be this negative 5 amps times this integral from 1 meter to 3 meters. That was the length of the conductor. And then I get this I hat cross I hat term was 0. Then I get I hat cross j hat. This is going to be k hat. And I'm going to get, this is dx times 8x squared. So this will be my 8. I'm going to put the 10 to the minus 3 on the 8 because I think it looks pretty that way. Then I have our x squared, and I like my dx at the end of the expression that we're supposed to be integrating. I think it looks more normal that way. Okay? And so then this 8, 10 to the minus 3, we can pull that out because it's constant, and we're integrating x squared dx. And this will be in the k hat direction. Are there any questions? So this is the big part of the effort, is to get it, set up.
Just one question for this.
Mm-hmm.
So previously for the magnetic field, you said for the
Yeah, I drew it backwards, didn't I? Hang tight. Let me fix this. It's supposed to be 3 in the I hat, and I drew 3 in the j hat. So it goes like this, and then it goes 3, and then it goes at 1, it's 8. It goes like this. It actually looks like this. Sorry.
Oh, for the magnetic field?
Yeah, I drew, I reversed. I don't know if that was your question or not, but when I looked at it, I saw it again. So. And then this one would be the same kind of thing. It would only be 3 this way, and then it would be, what was it, 72 this way? Something ridiculous like that. There we go. So. There we go. Sorry. All right, so what was the question?
So previously, whenever you do the right-hand rule, use the fingers for the velocity.
First, yes.
So for this case, you would use ds as your fingers.
Yes.
Right? Okay.
Right.
Okay.
Which is the I hat. So that's the fingers. And then we did I hat and j hat component. So I hat cross I hat is 0.
Right.
So that one we didn't need to worry about. But if we do I hat and then cross into j hat, So you either would sweep through that smallest angle, or you put your fingers in the first, out of the palm is the second, and then the thumb is the product. So fingers is the first, that's the I hat, this is the J hat, and then this is the product I cross J, which is K.
It's coming out.
It's coming out.
Okay.
Okay. All right. So then, and 5 times 8 is what, 40? And then we're going to integrate like this. And so then this will be integrating x, you increase by 1 and then divide. And then you do upper limit minus the lower limit. So this would be 3 cubed over 3 minus 1 cubed over 3. And then again, this is in the k-hat direction. So that would be 3 squared, which is 9, minus 1/3. So I guess if we put it back to thirds again, that probably would make more sense instead of reducing. So this is 9 minus 1/3. Or we could put this as what, 27 thirds minus 1/3. So that's 26 thirds. And so then our magnetic force will be negative 40 times 10 to the minus 3 for the milliteslas. And then this would be times, 26 divided by 3, and then in the k-hat direction. So we put that together, and we should be able to get our force in newtons, because everything was in SI units. And so what do we get? It's negative how many newtons in the k-hat direction?
Negative 3.46 k-hat direction.
10 to the minus 3?
10 to the negative 1, sorry.
10 to the negative 1. Okay, there we go. All right, cool. Good, good, good.